Okay, it's 11 a.m., so good morning, everyone. Welcome to ACOM seminar. It's my pleasure to introduce today's speaker, Dr. Christopher Holmes. Dr. Holmes is an associate professor in Earth, Ocean, and Atmospheric Science at Florida State University. His research examines the global cycles of air pollutants and greenhouse gases and interactions of both with climate change. His group builds and uses numerical models to understand chemical and physical processes that control the fate and impact of contaminants in the environment. Current topics in his group include ozone interactions with the biosphere, air quality and climate impacts of biomass burning, multi-scale modeling of atmospheric oxidants, changing Arctic chemistry, and biogeochemical cycles of mercuries. Dr. Holmes received an SF Career Award, and he is also a NASA New Investigator. Before starting, I would like to remind people following online that you can enter your questions in the space below the video at any time during the talk. And at the end of the presentation, I will read those questions to Dr. Holmes. And with that, I will leave the floor to Dr. Holmes.
Thank you very much, Ching. Plug this in. Okay, so, thank you very much for this opportunity. It's a real pleasure to speak to you all. I'm going to be addressing the issue of air quality impacts of fires in the eastern US. I know that there's a lot of expertise in fire science in this room and across NCAR, and really the western US in general in looking at fires, especially in the western US. But I'm going to be looking at fires in a somewhat different context, focusing on fires that look more like this, a prescribed fire in a pine savanna in Florida. Which nevertheless, despite their smaller size and less newsworthiness, it has a substantial impact on air quality. This work is the work of Holly Noel, who is a postdoc in my group, and Charlie Feit, who is a current PhD student, and many other colleagues on the NASA and NOAA FIREX-AQ science team, but especially Kevin Robertson at the Tall Timbers Research Station. So the reason that many of us, myself included, are interested in PM 2.5 and air quality is because of their impact on human health. And the map here is interpolated from a fusion of satellites and monitors and models to infer what the surface PM 2.5 is around the globe. And using data sets like this, it's now known that PM 2.5, ambient particulate matter pollution, is one of the leading risk factors for early death, falling within the top 5, amongst other things that we commonly think of as risk factors like smoking or high blood pressure. So air quality is a major factor along with those that are much more widely recognized. Ambient particulate matter is accounts for almost 8% of worldwide deaths. And within the US, it's somewhere in the range of 45 to 90,000 people dying per year as a result of ambient air quality. If we look at the current status of air quality and PM 2.5 around the US, we get maps something like this. This is a fusion, again, of models and measurements using a variety of predictors. But you see across the eastern US that concentrations are currently in the range generally of 9 to 12 micrograms per cubic meter on an annual average. Now this complies for the most part with the current National Ambient Air Quality Standards for PM 2.5, which is currently 12 micrograms per cubic meter on an annual average basis, or 35 micrograms for a daily average. But back in January, it has been proposed that that standard should be lowered to somewhere in the range of 8 to 11 micrograms per cubic meter, likely 9 to 10. And once you get to those levels, you see that across much of the eastern US, those areas may well be out of compliance with these proposed standards. Nevertheless, health effects are established at this point at even lower concentrations than the proposed standards. So let's take a look at what the driving factors are for this ambient particulate matter. And I'll take Florida as an example. This is the national emission inventory for the state of Florida, but other states in the southeast qualitatively look quite similar. These are the primary sources of PM 2.5, and the sectors are down here, so transportation, industrial fuel appear down here. But by far the largest source here is fires, which fall into the category of prescribed fires that are intentionally lit, wildfires that are burning out of control, and the National Emission Inventory categorizes agricultural fires somewhat differently. So fires are a large source of primary particulate matter, and let's take a look at what these fires actually look like in case you're not familiar. So this is the same image that I showed at the beginning. This is a prescribed fire in a pine savanna. These fires will burn the understory, which is here a mixture of grasses, ferns, and these are conducted for purposes of mitigating wildfire risk by burning off fuels in an intentional way so that they don't burn out of control. That's also carried out for land management and wildlife conservation to provide habitat that is suitable for a wide range of native flora and fauna, and also for forestry to maintain forests in an economically profitable fashion. So this is what most fires look like if you go across the southeast US. Low intensity, burning through the understory, leaving the trees largely untouched. Agricultural fires will burn through, obviously, an agricultural field. This picture here shows burning sugarcane fires, which I'll come back to at the end to look specifically at the impact of sugarcane fires. But generally these are carried out for the purpose of removing unwanted biomass from the field. Often that's after the harvest, but for sugarcane fields are actually burned before they're harvested. They also serve some purposes of preparing the field for the next planting, removing weeds and pests. Other fires will include land clearing. This is a woodpile following Hurricane Michael, a Category 5 hurricane, and there were large debris piles like this across much of the landscape in the southeast. But also, you'll see development resulting in land clearing and piles of biomass like this. And finally, there are wildfires. This is a wildfire near Pensacola that closed Interstate 10. And of course, this is distinct, from these large flame lengths and now burning the tree canopy. So if we come back to this, these are what the pictures that you should have in your mind of what fires look like in the southeast. So I want to look a little bit at why we do have so much prescribed fire in the eastern US, and also point out, I'll come back to agricultural fires at the end of the talk, but this is almost certainly much larger than what the National Emission Inventory has predicted. As far as the reason why we have these fires across the southeast, this map shows the mean fire return interval in the pre-European era. So down here across the southeastern US, you see that fires historically occurred every 2 to 6 years across most of the eastern US. So the landscape there, the vegetation, the wildlife is adapted for frequent fires. And so in the absence of prescribed fires, we have a high wildfire risk in the southeast US. In fact, the wildfire risk here is similar to sort of the well-known wildfire risk in, say, the California Sierras. So one way that we've looked at this in my group is to use state records of fires. The state of Florida has very good record keeping of all of the prescribed fires that are burned within the state. This happens because you are required by law to get a permit before lighting one of these. And so my group, and Holly in particular, has taken these data over a decade and looked at where these fires are happening and what their purposes are. So over here you see a picture of agricultural fires concentrated around Lake Okeechobee. These are the sugarcane fires. Silvicultural fires are spread across the state. land clearing happening where development is most rapid, and wildfires happening most in the Everglades and Big Cypress area. And when you add this all together, you get about 25,000 fires are burning each year in Florida, burning about 2.5 million acres. That's actually 7% of the land area of the state of Florida. So a tremendous coverage of that fire. And when you break it down, most of it, over half, is happening in forests. A small fraction, less than 10%, is wildfire. Now, I'm showing Florida, and that's just because Florida is the state with the best record keeping regarding fires. We know that the fire regimes are very similar across other southeastern US states, but Florida has the best and most open record keeping on these matters. So this is the state that we can show you the results for. But let's look at the time series of how these fires vary over time. So this shows the area of fires each year from 2005 through 2014. The area varies, so I've split it out here between prescribed fires and wildfires in red. You see some variation with a drought index here, the Palmer Drought Severity Index. So in dry years, there is more wildfire. In wet years, there is less wildfire. But notice that the prescribed fires are varying in opposition to that. So if there's a dry year, prescribed fires are scaled down because you don't want to burn if there's a large wildfire risk. In contrast, in a wet year, it's good for prescribed fires, and so there's more. So the effect of this is that overall fire area actually decreases in drought years. This is the opposite of what you expect from a natural climate control on fires. In a natural system, you would expect dry years would have more fire. Florida is doing the opposite, and so that's actually showing that prescribed fire policy is actually offsetting or interrupting that natural climate control on fires. So this diagram here is really showing a policy success that prescribed fires are having the desired effect of reducing wildfire risk. Now, Florida is 2.5 million acres. You might wonder, where are some western states? Well, here's the area of prescribed fires in California, about 125,000 acres per year. So, and California is obviously a much larger state in terms of land area than California. And so this sort of shows the gap in what California might have to do in order to reach the sort of level of policy action that the state of Florida is already taking on. So these fires are widespread, and they are happening here for these purposes of accomplishing these policy objectives. But if we're interested in air quality, I want to look at how well we detect these fires and how well they're represented in emission inventories. So this same study from Holly and my group looked at what the reported fire area was across Florida, and then what the fire area was in a couple of different satellite-based fire maps. So here's the GFED inventory. Here's one based on Landsat. And you can see immediately this contrast that the reported fires are much more extensive than we're seeing in satellite inventories. And that's because these previous satellite inventories were based on MODIS, Landsat, the prior version of the GOES satellite, and they just don't detect these fires. And the reasons we understand are that these are low-intensity fires burning in the understory, so there is the overstory of the forest that is obscuring the view. There's frequent cloud cover in the eastern US, which again obscures it. They're also very short duration fires, so if the satellite isn't passing overhead when the fire burns, you may miss it for that reason. But the good news is that the latest version of the GOES satellites, GOES 16, 17, and 18, are much, much better at detecting these. And VIIRS is as well, although not to the same extent. So this is showing across a range of fire sizes, what fraction of those fires are detected by GOES in orange or VIIRS in purple. And we see that for all fire sizes, GOES is detecting over 50% of the fires, and for the larger fires, 80 to 90% of the fires. So this is a major advance over prior things. And VIIRS, while doing much better than MODIS and other things, is still much lower detection efficiency. And we can understand this very simply in terms of the number of views that you get per day. So this is a picture from MODIS for one day, and you get a swath like this twice a day, or if you aggregate over multiple satellites, maybe you get up to 8 swaths per day. In contrast, GEOS-16 gets a view over the entire US every 5 minutes. And so you just have a much better chance of detecting those fires, even though the pixel size resolution of GEOS is not as high as it is for VIIRS. So most emission inventories have been based on MODIS or MODIS and VIIRS, and there's really only one inventory, the HUR inventory, that has used GEOS. And so what we're doing is we are developing a new fire emission inventory that's based on GEOS because of this much better detection efficiency. So this inventory is the GEOS-16 Eastern US Fire Emissions Inventory. It's GEUFE is the pronunciation. And it uses a standard approach where the emissions are equal to the fire radiative energy that's detected by the satellite times the ratio of biomass burned per fire radiative energy that comes from field studies multiplied by an emission factor which comes from field and laboratory studies. The first two terms here are, in our case, provided by collaborators Aditya Kumar and Brad Pierce at Wisconsin, and my group's main contribution is to refine these emission factors. And emission factors in most inventories are based on fairly crude representation of landscapes. There are, in many inventories, about 4 to 6 broad land cover categories that might be savanna, extratropical forest, and these are coming from global compilations of emission factors. You know, some of these are well-known studies, Akagi and Andre. But for the US, we have extensive fire studies, and we can make use of those. So GEUFE uses 27 publications, which summarize studies of 200 prescribed fires and laboratory burns, all focused on fuels that are found specifically in the eastern US. And FIREX-AQ is one of those sources of those emission factors, and they're also kind of summarized over here. So we're able to provide a lot more detail, and I'll show why this matters. So we have 5 forest types, we have 3 different types of grasslands, we have 7 different types of crops, we have a wetland type, and we have 3 different types of savanna and shrublands. When we look at which of these are most important in terms of fuel burned, we see that over here, woody savannas account for most of the dry matter consumed across the eastern US, with croplands being a second and other types of grasslands being third. And these maps show where these landscape types are found. So we can see that woody savannas are found really scattered across the entire eastern US. So let's look at why it's important to provide this information about and more refined detail about fuels. So let's take woody savannas as an example. Okay, so they're extensive across the eastern US. Within GEUFE, we've looked at these studies. These are very well studied fires. Because they're so widespread, we have both field and laboratory studies of these. And we find, just taking organic carbon as an example, that there's about 10 grams per kilogram of OC emitted from these. And this is what GEUFE uses, but most other inventories for this area would classify these in the same category as an African savanna. And the OC emissions, according to Akagi or Andre, are in the range of 2.6. So a vast difference in terms of these emission factors. The reason being that these woody savannas in the eastern US have a lot of pine needles on the ground, and if you've ever had a campfire and thrown pine needles on it, you know that they produce a lot of smoke. So taking this into account, we believe leads to a better understanding of those emissions. To take another example, evergreen broadleaf forests across the US, these are not, these are really pine forests with a broadleaf understory. And these will have an OC emission factor of about 7.5 grams per kilogram. But most other inventories would be using the same evergreen broadleaf emission factor as for tropical forests, which visually look very different, and the plant species are very different. To take another 2 examples, let's look at prairies. So we have found that there's enough information to differentiate between different types of grasslands in the eastern US. So there are tall grass prairies found in the Central Plains, there are short grass prairies found in the southeastern US, and they have substantially different emission factors, with the short grasses having a much lower emission factor, and the tall grasses having a very large range depending on whether those prairies are burning in the wet season or in the dry season, with wet season fires having much higher emissions. To take another example, just looking at crops, the FIREX-AQ data and multiple other past studies have established different emission factors for different crop types. So corn will have a lower OC emission factor than rice. And we're able to establish where those different types of fires are happening using a combination of VIIRS and the USDA Cropland data layer, which specifies year by year which crops are grown in which places across the US. So we are taking those and establishing maps that show, in general, in September, this is where corn is burned across the Mississippi River Valley, and here's where rice is burned. So we can see that there's a spatial difference in where those fires are happening. And if you're interested, here's the seasonal cycle of those different crops, and so you're seeing that those different crops are burning at different times of the year. So if we put this together and look at what the total emissions are, here's a comparison of 9 different emission inventories. GEUFE, our new inventory, is shown here. We have a huge range here. So on the high end, we have GBEP-X at 1.3 teragrams of organic carbon per year. At the low end, we have GFED at 0.05 teragrams per year. Some other notable inventories, FIN has been developed here locally. This is sort of on the low end. We have the National Emission Inventory, which is on the same magnitude as FIN here. GEUFE is really at the high end, quite similar to QFED in terms of overall scale, and the spatial pattern is reasonably similar. So there's a 26-fold range in emissions between these inventories. One thing that we found, we've dug into why do these inventories differ, and some past studies have suggested that the fuel consumed is the main reason for differences. But if we look at a wider range of inventories, we really see that it's both emission factors and fuel consumed that is driving this range of estimates. So GEUFE is near the upper end, and I want to compare it here. Note this, again, this comparison with QFED. Because QFED is based on MODIS detections, but then they have a scale factor that they apply so that their model better matches the observed aerosol optical depth. And so they have actually multiplied the emissions that they get in their process inventory by a factor of about 4.5. So they've scaled up their emissions by 4.5. GEUFE, in contrast, is using better fire detections from GOES and emission factors that are more regionally appropriate. And so we have a process-based model that gives you largely the same result as QFED. So now we have a process-based justification for what QFED was doing using scale factors. We're going to evaluate this using a model, the GEOS-Chem model. We're using the highest resolution that's available, 1/4 degree resolution, and we're using the greatest degree of sort of aerosol complexity that's available in GEOS-Chem, the so-called complex SOA chemistry. The advantage of using this is that this aerosol chemistry has been previously evaluated in this area for the prior Seekers campaign, so evaluated extensively and shown to perform quite well outside of fires. So we have some confidence that this aerosol scheme is suitable for simulating aerosol within this region. So let's take a look at the data sets that we are using to evaluate this. We have the observations here from the FIREX-AQ campaign. These consist of 7 flights that were based out of Salina, Kansas, flew especially over the Mississippi River Valley, but also sampled fires in the central plains of the US, as well as wildland fires in the southeastern US. Sampling was done from the NASA DC-8 for these fires, and about 87 prescribed fires were sampled in the eastern phase of this campaign. I'm going to focus our evaluation on data that was collected with the high spectral resolution LiDAR on this aircraft, and this consists of a laser that's shown down beneath the aircraft. Light is scattered and reflected back by aerosols, and so the observations give you a vertical profile along the plane track of the aerosol scattering. If you integrate the aerosol scattering vertically, you get the aerosol optical depth. And this shows measurements from the LiDAR from one flight over the Mississippi River Valley. I'll show the path more clearly on the next slide. And we're also able to sample the model in the same way along the same flight track, giving this down here. So let's look at what these show. For one particular case study, this is our best case study for looking at the integrated emissions of fires from FIREX-AQ. So this flight consisted of a repeat sampling from south to north across the Mississippi River Valley, once in the morning to sort of give you the pre-fire background, and that's shown in blue here, and second in the afternoon, shown in red here. And we have integrated the aerosol optical depth below the aircraft, and some of the differences that you see between the morning and the afternoon are, well, the afternoon contains a lot more spikes, indicating that you're seeing fresh emissions that are dramatically increasing the aerosol optical depth. There's a slight increase in the optical depth when you average over the entire track, and this increase is happening despite the decrease in relative humidity. So when relative humidity falls, you expect that the aerosol will contract, giving off water, and reducing aerosol optical depth. So despite the falling relative humidity, the overall aerosol optical depth actually increased over this time period, again, as a sign of the emissions of aerosols from fires. And we established that it's from fires because in our model without any fire emissions, we predict that the aerosol optical depth would basically stay the same over the course of the day, and yet the observations show that it increased. So these are a set of 5 different model simulations showing the aircraft path here. The emissions are these squares, and the inset numbers show the simulated aerosol optical depth averaged along the flight track in the morning in blue and afternoon in red. Okay, so without fires, we had about 0.09 optical depth morning and afternoon. We get still an underestimate if we use GFED, FIN. However, if we use GEUFE or QFED, we get an increase that is quite similar to the observations. And GBEP-X predicts both too much aerosol optical depth in the morning and too much increase over the course of the day, indicating that their emissions are almost certainly too high. Besides pointing out that agreement there in the averages, I also want to mention that GEUFE and GEOS-16 were the only satellite and emission inventory that actually includes all of the fires that were sampled by the DC-8. So all of these other inventories, because they were based on other satellite products, missed some of these fires. Now, this is just one case study, and you shouldn't be satisfied with that, so let's look more broadly. First off, this is looking at all of the LiDAR data over the eastern US portion of FIREX-AQ and showing scatter plots of the observed aerosol optical depth on the x-axis of each of these panels and the simulated aerosol optical depth on the y-axis. And again, we see sort of the pattern that will repeat here in each of these comparisons is that the model with FIN, GFED, or without any fires tends to underestimate the aerosol optical depth by about 15 to 25% in this case. GEUFE and QFED have minimal bias, and the slopes are of the correlation are quite close to 1-to-1. And again, GBEP-X predicts too much aerosol optical depth. Now, again, this probably still isn't convincing because how do we know if it's the fires that are driving this correlation or other factors? So we've dug into that by using a combination of AeroNet which provides aerosol optical depth at these stations here in blue and red dots, across the eastern US. And we have segregated the aerosol optical depth measurements based on whether the NOAA hazard management system indicated that there was a smoke plume over that area. So the NOAA HMS product is something that is provided more for emergency managers and the public to indicate where there's heavy smoke exposure. It doesn't cover all smoke exposure, but it shows where there's a sort of visually obvious plume that is picked up by a satellite. And over here, these gray areas show just for one day all of the smoke plumes that were indicated by HMS. And we see that on this particular day, one of these AeroNet sites was within a plume, and so we think that that AeroNet observation is going to be smoke impacted, and the others, which are shown in blue, are going to be less smoke impacted. So what we can do now is we can take these AeroNet observations and we can segregate them into, in green here, we have the observations that do not have smoke. In blue, we have the observations where HMS indicated that there was a smoke plume. So we see that when there was a smoke plume present, the aerosol optical depth was larger than it was in other cases. That's, again, indicating that HMS is giving us at least some indication of when there is smoke exposure. If we look at the model outside of the plumes, we see that, well, there's not a whole lot of difference between the model with different inventories. So regardless of whether you use GEOFE-X down to no fires, the mean and median in the model are kind of close to where they are in the observations. And this indicates that, outside of heavy smoke exposure, this model is doing a good job of representing aerosol concentrations. And this is, again, providing support that this model is representing non-smoke emissions reasonably well. If we then focus on the smoke emissions, the observations during smoky periods, we now have these blue areas over here, and we can now see that there's a lot of distinguishing between the different models. So the observations suggest the mean and median are around here, and again, GEOFE-X predicts too much aerosol when there is smoke plumes present. These inventories over here predict too little smoke, and again, QFED and GEUFE are in the Goldilocks zone where they are providing the best match to the mean and median of the observations, both in smoke and outside of smoke. And down here is the bias shown, the model bias shown in the areas without smoke, so a 3% bias for GEUFE and a 7% bias in smoky periods. So GEUFE is again providing the best match to these observations. We've also looked at the surface PM 2.5, and the story is largely the same. If we look at all of the EPA AQS sites, there are about 310 of them across the eastern US. GEUFE provides a pretty good match on the mean to the ambient air quality of PM 2.5, and here's the correlation plot. If we compare that with GFED, the slope and bias are indicating that there is not enough aerosol PM 2.5 in these cases. So I hope this provides some convincing to you that the model with the GEUFE emissions is providing a good representation of smoke emissions across the eastern US. And again, I want to reinforce that we're looking at the impact of smoke emitted in the eastern US. So we're not even looking at smoke that's transported over long distances from the western US. And if we look at where that smoke is having an impact and how big that impact is, over here we've got a map showing the enhancement of PM 2.5 across the eastern US. We are seeing across this region about a 2 to 5 microgram per cubic meter increase in annual mean PM 2.5 due to these fires. That's out of a current ambient air quality standard of 12. So we're looking here at 20 to 40% of the allowable limit. And if that limit comes down, well, then you're even closer to it. If we aggregate things across states, we see that Florida, Alabama, and Louisiana are the most smoke impacted states, and New Orleans kind of stands out as being the most smoke impacted city in the eastern US, with some other major cities also being not far behind. But note that these smoke impacts, these are in the several microgram per cubic meter range. This is actually comparable with what the smoke impacts are on average in the western US. So the extremes are not as bad as in the western US, but the mean smoke exposure is actually comparable in the eastern US to the western US. There have been several studies that have used HMS to identify when smoke is present in the eastern US. And so we've done that with our model to say, well, what fraction of the smoke exposure in the eastern US is actually captured by those HMS smoke plumes? And we find that it's no more than 50%. So if you are using HMS to detect when people are smoke impacted in the eastern US, you're missing about half of the smoke exposure. And that's because most of these smoke plumes are from smaller fires that are not picked up by the HMS system. I want to turn back to the topic that I mentioned at the beginning about those agricultural fires potentially being underestimated in the National Emission Inventory. And I'm going to do that with a case study of sugarcane fires, which are a longstanding air quality issue in Florida. And this is what a sugarcane fire looks like. You'll have a very intense, very thick smoke plume that generates pyrocumulus, and it'll burn for 20 minutes, and then it's over, and then the next field burns when they move on to that. If we map out where sugarcane fires happen across Florida, they are concentrated south of Lake Okeechobee in the Glades area, or what we're calling in this study the sugarcane growing region. And besides having a lot of sugarcane fields, this area is also notable for being a very low income area and having having a higher non-white fraction than the nearby coastal communities. In terms of the number of fires, on average, there are about 10,000 sugarcane fires that burn each year. They burn about 400,000 acres, and they emit about 5,000 tons of PM 2.5. This is actually pretty close to the PM 2.5 emissions from all of the vehicles in the state of Florida, which is about 6,000. So this one agricultural fire type is producing about as much smoke as all of the vehicles, but it's concentrated in a small area. In contrast, the National Emission Inventory gives an emission of about 3,500 tons for all agricultural fires across Florida. So what we've found using locally specific emission factors is that this National Emission Inventory must be underestimating the fire emissions because there are a lot of other fire types besides sugarcane fires that are happening in Florida. The sugarcane industry has claimed for many years that they do not have an impact on air quality in this region or anywhere else. And so this has been in the news and there have been lawsuits, and so we took a look at this, at what the data suggest. So we looked at the surface PM 2.5 monitors, and we segregated them by the two monitors that are in the sugarcane growing region versus the others that are sort of spread across the Florida peninsula outside of that region. And red indicates the winter harvest time, and blue indicates the summer non-harvest time. And we see that within the sugarcane growing region that the winter PM 2.5 concentrations are higher than they are in summer. In contrast, if you go anywhere else in the rest of Florida, you find that summer PM 2.5 concentrations are higher than they are in winter. So something about the seasonal cycle is qualitatively different within the sugarcane growing region than it is elsewhere. We've used satellite data. This is taken from Aaron van Donkelaar's satellite-based data set of PM 2.5. And here we can map out the winter versus summer change, so the seasonal cycle, across the Florida peninsula. And we see that the area where winter concentrations are higher than summer is really co-located with the sugarcane growing region. So both from the surface monitors and from satellites, it's indicating that something is different in the sugarcane growing region. And really the only substantially different thing here is these sugarcane fires. So we looked at this from a process-based model. So we ran high split simulations, starting from all of the known locations of these fires, because every fire here is permitted. And this is a Landsat image here showing some of these smoke plumes. This is a 2-kilometer distance bar down here, and so you see that these smoke plumes are on the order of 1 kilometer or so across. So we used high split to provide that high spatial resolution. We provided a number of improvements to high split to simulate these. We looked at the timing of these fires using the diurnal cycle of fire detections from GEOS-16. We added a representation of smoke plume rise based on the MISR satellite aerosol height product, and we are simulating about 10,000 dispersion particles per hour per fire for each of those, again, 10,000 sugarcane fires. Again, here's one of those fires, and they're burned specifically when they know that the weather conditions will support lofting of these smoke plumes. So I don't want to suggest that these fires are burned willy-nilly. They're burned under very specific weather conditions that maximize dispersion. And so you see, if you are there for one of these fires, that the smoke really does go pretty much straight up. So that's good. It's actually minimizing the impact on surface. But it's not as though it's going to be zero impact on the surface. So we've looked at what would the impact be with a range of different plume rise methods. And by default, the high split model tends to use a Briggs plume rise, which gives a low estimate of the surface concentrations, and then if you emit everything at the surface, you'll get a very high surface impact. So we're going to be sensitive to these vertical plume rise, and so what we've done is we've taken aerosol height from the MISR instrument, and we've created a histogram here showing what's the expected initial vertical distribution of smoke following one of these fires. And what we find is that most of the smoke, the peak amounts, are lofted to about half of the boundary layer height. There is about 5% that escapes the boundary layer, about 95 is captured within it, but at least immediately downwind, there's a fairly low surface concentration. Of course, as this advex downwind, there's vertical mixing, and this initially lofted smoke will be transported down to the surface by boundary layer turbulence. Looking at these fires over almost a decade of time, we simulate an increase in the PM2.5 concentrations that's concentrated in the sugarcane growing region, about a microgram per cubic meter from these agricultural fires. And just zooming in here on the sugarcane growing region, we find that that's about 7% of the PM2.5 within this region. I'm not saying it's dominant. There are obviously other sources. But this is a meaningful contribution. And this spatial pattern is consistent with the magnitude and spatial extent that's inferred from the surface monitors and from the satellites. Of course, the reason that there's been public concern about these fires has been the health impacts. And we looked at this in terms of mortality impacts using the GEM concentration response functions, which specify the mortality hazard ratio for 5 different health outcomes that result in death. And we found that sugarcane fires are likely responsible. Well, here's the increase in mortality per 100,000 residents. And across South Florida, we estimate that there is between 1 and 6 deaths per year, 95% confidence interval. And that specifically within Palm Beach County, where most of these fires occur, that there's up to 2 deaths per year. Again, 95% confidence interval for these. So my role in this, and I want to be clear, I probably don't have to say it to this audience, but it's to provide information that can allow residents of the glades to make decisions for themselves about what they want to do. Sugarcane is a major industry for this area. It's almost a $1 billion industry. It's a major employer in the area. At the same time, the impacts are not zero, as the sugarcane industry has claimed. And to be fair, this is 7% of the PM2.5. There's a lot of other sources that are responsible for 90%. So if you're thinking about health impacts, you want to think about the overall role of sugarcane fires relative to other sources like vehicles, other industries, residential and commercial. So I'm not drawing any conclusions here about what should or should not be done regarding these. This study has gotten a lot of public attention in news and also triggered some really vehement responses from the sugarcane industry and large public records requests. And so I think it's worth mentioning here that the public records request that we got regarding this study, the university attorney tells me is the largest public records request that they've received in many years. And a reporter from NBC told me that she'd gotten more blowback from the story that she wrote covering our story than she had for anything that she'd gotten in her 20-year career at NBC and the Washington Post. So this is a hot button and raw nerve topic within Florida. Okay, so with that, I want to circle back to what my conclusions are here. So the things that I'd really like you to leave with are recognizing that GEOS 16, 17, and 18, the latest GEOS satellites, detect more prescribed fires than past satellite instruments, and that when you use those with region-specific emission factors, which you should when they're available, you get a better estimate of emissions. GEUFE, our new inventory based on those things, is a process-based inventory that supports the high emissions that have been inferred by QFED, but now we can do it in a process-based way without scale factors. The observations of aerosol optical depth and PM2.5 support those high fire emissions and suggest that the contribution of eastern US fires to air quality in the eastern US is 2 to 5 micrograms per cubic meter. Most of these are prescribed fires, and as the PM2.5 standard is lowered, it's going to become much more difficult to manage these fires in these landscapes, which are, again, fire prone, in light of these more stringent PM2.5 standards that are coming. So all of us will, I'm sure, be talking a lot about these strengthened and lowered standards over the years to come. And I'll leave you with that. Thank you.
Okay, we'll first take questions in the room.
Hi, great talk, very useful. Thank you. I have two questions. So the first question is, for FRP-based emission inventories, as you mentioned in this region, the prescribed burning, therefore understory burning there will be a lot. I wonder, because of the overstory cover, I wonder would that be a concern for FRP-based inventories?
I think it's a concern. I think it's certainly worth looking into that more. I don't have a firm answer about that, but you're right to be skeptical. We are seeing that we're able to detect the fire area using GEOS 16, but we could certainly look more into that in future work. Yeah.
Okay, sounds good. And my second question is just out of curiosity. So during FIREX-AQ, I noticed over some cropland, the residual biomass were gathered together and piled up. I wonder if that's the way those biomass would be burned. Because if that's the case, the burn area and the fire size would be very small and hard for a satellite.
Yeah, so those pile burns are really an argument in favor of using fire radiative energy rather than burned area, because that fire is still going to be emitting that radiant energy regardless of whether the biomass is collected together or spread out. Those pile burns tend to be for land clearing fires, not for crop burning. So crop burning is usually done without collecting the biomass first.
I see. Thank you.
But certainly they're both common practices.
Thank you.
This is really interesting. Thank you. One of my questions, I'll ask one for now, is about your regional specific emission factors. And I'm curious sort of what the balance is between lab and field data, and whether you've had to scale your lab data at all, or how, and if you've evaluated the ability of the lab data to represent the field.
Yeah, so there's a lot of expert judgment in that. We, in terms of numbers of studies, we relied more on the field studies. I would say numerical-wise, there's sort of roughly equal numbers of field and laboratory studies, depending on which fuel type. We did use expert judgment in selecting the lab data. You might have a lab study that burned, say, 3 different types of fuels that are all found within a pine savanna. But one of those may be, by far, when you go out in the field, the dominant fuel type. And so we selected the lab studies that used the predominant fuel types. So yeah, I mean, you obviously know that there's a whole lot of a considered judgment that goes into constructing those, and I think that's, you know, a longer conversation about diving into those details. But in general, we noted consistency between the dominant fuels that were burned in a lab versus the field studies.
Thanks for the talk, very interesting. You've shown a couple of comparison between models and observations, satellites or ground-based, and you showed very nicely how GEUFE does a really good job at capturing the average. However, the scatter in there is still pretty big. I'm curious to hear from you what's causing the scatter and what can be done to reduce that.
Mm-hmm. So that scatter is certainly going to be due to errors in model meteorology, dispersion, wind direction. It's also going to be due to limitations of model resolution. The model resolution is, we think, good enough to capture the average plume dispersion, but not sufficient to resolve individual plumes, because we are working with a sort of 25-kilometer model, and these smoke plumes, some of them are that size, but some of them are much smaller. So it's my expectation that those are the 2 dominant factors.
Thank you. Do you have a directory where I can download real-time results?
Do you have a directory where I can download real-time results hourly from the GEUFE inventory?
No, we don't have that at this time. If anybody has a pile of change that they'd like to contribute to that effort, we're happy to work on it. Sorry for the cheeky answer. That would be something we would like to do, but it's not within our abilities right now.
Okay, cool. We have a question online from VIIRS. Thank you for the great talk. I have 2 questions regarding the GEUFE inventory. First, what is the horizontal resolution? And second, does it have diurnal profile since it's based on GEOS? And could it be the reason for a better performance on morning/afternoon enhancements? Sorry if I missed this.
Yeah, so the horizontal resolution of GOES is 2 kilometers, so that's the resolution of our emission inventory. We are degrading that to the model resolution because the model is not at 2-kilometer resolution. The diurnal profile is, we are using a mean diurnal profile. Certainly that is something that we could look at in future work. We do think that because the observations are going to miss some fires because of cloud cover or other factors, that we may be better off using a mean diurnal cycle than using specific 5-minute intervals when a fire is detected. And yes, sure, that could be could that be the reason for the better performance? Yes, that could contribute to the better performance. When we have evaluated other inventories, we have used the diurnal cycle that's provided in those inventories if they do provide one, and we have used a generic one if they don't. So certainly, absolutely, the diurnal cycle will contribute to the comparison of morning versus afternoon. I think specifically for that case study in the Mississippi River Valley, I would say that just the lack of fires detected in each of the other inventories is going to be a significant factor as well.
Thanks, Chris, for your nice talk. I'm thinking about what you said about the prescribed burn area being much larger in Florida versus California. The prescribed burning in California, I think, is typically in the wildland areas. Prescribed burns in wildland areas, I think, are generally run by state or federal government agencies. Do you know who is actually doing the prescribed burning in Florida or in agricultural regions? Is it the individual, companies or landowners? You said it's permitted by the state, and is there something that could be some knowledge that could be transferred from whoever's doing that prescribed burning to help keep them safe in wildland areas as well?
Mm-hmm. So I think there is a big opportunity for knowledge transfer, and that is happening at least to some extent. There is a national prescribed fire training center that's located in Tallahassee, where they do bring in people from across the country to work on training for these things. In terms of who conducts the fires in Florida, a lot of the fires are conducted on federal land or state land, and so they're by the U.S. Forest Service or the State Forest Service or the Department of Defense. Those are the largest land managers in Florida. But there's also a very substantial contribution by private land owners, and that is enabled by, at least in part, by the liability standards. In Florida, if you are a certified prescribed burner and you are following established best practices and you have a permit, you are not liable if a prescribed fire goes out of control and becomes a wildfire. In Western states, my understanding is that if you light a fire, you are responsible for its consequences. And that liability standard is a major impediment to at least private landowners conducting prescribed fires on their land holdings.
Chris, thanks for a great talk and for reminding us why sugar is bad for you. I have a question related to that, which is there's a lot of sugar grown in various countries, Brazil, India, Thailand. Mm-hmm. I would assume that burning of this type is done frequently, just purely for agricultural, ease. So you're nodding your head. So please tell us what you have thought about with regard to sugar production of dangerous 2.5 elsewhere.
Most other countries that harvest sugarcane have stopped burning sugarcane. Brazil has stopped, Australia has stopped, Hawaii has stopped. In Cuba, it's still widely practiced. But the US and Cuba are the only major sugar growing countries that continue to practice burning pre-harvest.
Why did the others stop?
Air quality.
Okay, thank you everyone for joining, and thank you all for the questions, and thanks Chris again for the great talk, and we'll see you next week.